Hello, this is Group 7's presentation for the Calc 1 final project, the shape of a can. We know that the materials for the cans are cut from sheets of metal. The cylindrical sides are formed by bending rectangles, and these rectangles are cut from the sheet with little or no waste. But if the top and bottom discs are cut from squares of side 2R, this leaves considerable waste metal, which may be recycled but has little or no value to the can makers. If this is the case, show that the amount of metal used is minimized when h over r equals to 8 over pi, or approximately 2.55. So we know that the material for the cans is cut from sheets of metal. The cylindrical sides are... So since we know that the size of the squares are 2r, we can see that the amount of metal needed to make one lid, either the top or bottom, is approximately 4r squared, or 8r squared for both top and bottom. Thus, we can determine the equation to create one full can is 8r squared plus 2 pi rh, where 8r squared represents the top and bottom, and 2 pi rh is the total surface area of the size of the cylinder. We know that the equation for the volume of a cylinder is pi r squared times h equals to v, where v represents volume. By moving some variables around, we can see that h equals to v over pi r squared. Now that we have a value for h, we can plug it into the previous equation. The updated equation for all the metal needed to make one full can is now 8r squared plus 2 pi r times v over pi r squared. We can factor out the pi and the r to simplify the equation to 8r squared plus 2v over r. To find the critical points of this equation, more specifically the minimum of this equation, we need to take the derivative of it. By using the power rule, 8r squared becomes 16r, and 2v over r becomes minus 2v times r to the power of negative 2, which can be simplified into minus 2v over r squared. Finally, we can plug in our v value, which, if you recall, was pi r squared times h, into the equation, turning it from 16r minus 2v over r squared into 16r minus 2 times pi r squared h over r squared. After canceling out the r squared from both the numerator and the denominator, we are left with the equation 16r minus 2 pi h equals to 0. By isolating the h and the r by adding 2 pi h to both sides, we're left with the equation 2 pi h equals to 16r. Then we can divide both sides by 2, leaving us with pi h equals to 8r. Then we can divide both sides by r, and we're left with h over r equals to 8 over pi. Question number 2 says a more efficient packing of the discs is obtained by dividing the metal sheet into hexagons and cutting the circular lids and bases from the hexagons. They're asking us to show that if this strategy is adopted, then h over r equals to 4 times the square root of 3 over pi, which is approximately 2.21. So the goal here is to achieve less waste as compared to question 1, where we were using square sheets of metal and h over r was equal to about 2.55. After drawing a small diagram, we can easily visualize and label the sides of the hexagon. We can label each of the 6 side lengths as a and the radius r. Referencing back to the first question, we know that the equation for the amount of metal needed to make one full can, including the top, bottom, and middle, is equal to 2 pi rh plus 3 times the square root of 3 over 2 times a squared times 2, where 2 pi rh is the surface area of the cylinder, and 3 square root of 3 over 2 times a squared times 2 is the formula to find the area of the hexagon. The reason that we are multiplying that part by 2 is because we need to account for both the sides, top and bottom of the can, and not just one side. In an attempt to remove a from the equation altogether, we can use it to find the radius. We know that the formula for the radius of a hexagon is r equals to the square root of 3 over 2 times a. Since we are trying to get rid of the a squared, we can square the entire equation, leaving us with 3 over 4 a squared equals to r squared. By removing the 3 over 4 from both sides, we have our finalized equation, a squared equals to r squared times 4 over 3. Now that we have a value for a squared, we can plug it back into the full equation. The updated equation for the amount of metal needed to make one can is now 2 pi rh plus 3 square root of 3 over 2 times r squared times 4 over 3. By canceling out the 3's in 3 square root of 3 and 4 over 3, as well as the 2's in 3 over 2 and 4 over 3, we are left with this simplified equation, 2 square root of 3 times r squared. Just like how we did in question number 1, we need to use the equation to find the volume of the cylinder, which is v equals to pi times r squared times h, and transform that into a function of h. It then becomes h equals to v over pi times r squared. We can then plug this formula for h into our larger function, turning it into 2 times pi r times v over pi times r squared plus 2 times 2 square root of 3 times r squared. We can cancel out the pi and r, turning the equation into 2v over r plus 4 squared root of 3 times r squared. The next step is to take the derivative of this equation. 2v over r again becomes minus 2v over r squared, and 4 squared root of 3 times r squared becomes 8 squared root of 3r using the power rule. We must also remember to set this equation equal to 0 because we are trying to determine the critical points. Now we can again substitute v and move the 8 square root 3r to the other side of the equation, making it minus 2 times pi r squared h over r squared equals to negative 8 square root of 3r. We can cancel out the r squared from the side, making it from both sides, making it negative 2 pi times h equals to minus 8 square root of 3r. Then we can divide both sides by 2, giving us pi times h equals to 4 square root of 3r. Finally, by dividing r and then pi, we are left with the final equation, h over r equals to 4 square root of 3 over pi. Since this value is less than the previous value from question 1, we are indeed saving metal in the process of making the cans.
By now, after solving problems 1 and 2, the h over r values are closer to the ones found on the supermarket shelves. But there is one factor we have yet to account for, which is that little lip that kind of bends and wraps around the ends of the can, which would make the radius larger than r, increasing the h over r value. In problem 2, we propose cutting the disc from hexagons, where then the total cost would be proportional to 4 square root 3 r squared plus 2 pi r h plus k times 4 pi r plus h. The 4 square root 3 r squared is the area of the hexagon. The 2 pi r h is the area of the cylinder. And when we have k 4 pi r plus h, our k value is basically just the cost over length of joining the sides to the lids. And of course, h would be height. The 4 pi r is found with 2 times the circumference because we have 2 lids to account for. This formula is the cost of joining the top, middle, and bottom of the can together. Our goal is to show how the formula is minimized to cube root v over k equal to 2 pi minus h over r over pi h over r minus 4 square root 3 times cube root pi h over r. This would tell us the volume is proportional to the cost of joining the parts together. From the formula, we can use the power rule to find the derivative, which we calculated to be 8 square root 3 r minus 2v over r squared plus k times 4 pi minus 2v over pi r cubed. Our volume should also include the value of hr, or h over r, so we can rewrite v to be equal to pi r squared times h2 to be equal to v equals pi r cubed h over r. Once we isolate r, we get r equals cube root v over cube root pi h over r. Once we do that, we could set the equation to 0 to find the critical point. This will help find the minimized equation when the derivative is equal to 0. We can begin simplifying. The first step is factoring out 2 from x prime. Step 2 is plug in v. From there, we cancel out the commons, then factor out k and isolate. The next step includes dividing both sides by r, then dividing both sides by pi h over minus 4 square root 3. Then we multiply both sides by cube root v over k, cancel out the commons once more, and substitute v. By the end, we have the cube root v over k minimized formula. We can also note with the equations that there's something over r in each of them. these will show that there would be some concave up where the minimum point is the critical point when the derivative is 0.
So part 4 is asking us to plot the cube root of v divided by k as a function of x equals h divided by r, and use your graph to argue that when a can is larger or joining is cheap, we should make h divided by r approximately 2.21. But when the can is small or joining is costly, h divided by r should be substantially larger. So this part of the question is all about graphing our results. Taking what we've got from question 3, we substitute h divided by r for the x-axis value in order to make it a graphable function. After simplifying our answer and plugging in x, this gives us the cube root of pi times x, parentheses 2 pi minus x, divided by pi x minus 4 times the square root of 3. And we now have a graphable function. When drawing up the graph, we label the cube root of v divided by k the y-axis value of the graph, and we also relabel h divided by r as the x value on the actual graph. And looking at the graph, there's a vertical asymptote at 2.21. The line also curves downward. And examining the graph shape, we can see that it supports the question's argument. Larger cans or cheaper joining is represented by larger y values corresponding to x values closer to 2.21. Meanwhile, smaller cans and expensive joining is represented by smaller y values, which correspond to larger x values that increase beyond 2.21.
Hello, my name is Wyckoff Higgins, and today I'm going to be analyzing, in the context of my group, the question 5 for the CAN project. So basically, what question 5 is asking is, it states that our analysis shows that large cans should be almost square, but small cans should be tall and thin. And it asks us to take a look at the relative shape of the cans in the supermarket, as well as analyze like the conclusion, if the conclusion that we made is true in practice, if there are exceptions, and if we can suggest reasons why small cans are not always tall and thin. So I thought this was actually really interesting and like fascinating when I was looking at the rest of the project, because here in the project we're looking at the most economical shape for the can and how much money we can save in specific designs of the can. But I feel like in regular like human living, we're not always analyzing the costs like efficiency. We're looking at what is most cost effective, yes, but also what is most ergonomic for human storage, and also like storage, display, and also just general use in the kitchen. One reason I can think of that like this conclusion isn't really the most common used one in society is that cylinders are like just true cylinders are the most ergonomic shape to hold. Like it just, you can just mold your hand around a can, small, thick. It's way easier to hold a circle than it is to hold a square. And also when you're trying to open a can, like with a can opener or just I guess with a fork or whatever you try to open your cans with, a can opener won't really work around a quote unquote almost square like can. All those cans would need pull tabs, like how Spam cans need them. I went to the grocery store today to analyze this because I wasn't sure if these photos were actually correct, because I don't really pay much attention to cans because obviously, but a lot of cans that were even almost square or sort of square had pull tabs, and that got me thinking like you need one tool to open all of these circles. This is the uniform design for cans. But when you look at like a Spam can or something like that, you have to do the pull tab, and that would create more waste within the world, especially if those metals aren't being repurposed, and especially if it's like a one-time use of like, oh, I have this can, I'm going to throw it in the trash, not even to be recycled. I also thought it was interesting that there are a lot of exceptions to this rule. I mean, also this design is very good for branding. Like this stack of cans is very different from this stack in color and also creation, and the label creation is very similar, like universally. And even though it's not really the most efficient way to stack and hold cans, it's certainly like it's probably easier to create these cans and easier to stack them than the ease of creation of quote unquote almost square cans and stacking almost square cans within a uh, shelf like this. Probably the most efficient way to store these cans would if they're hexagonal or something, but circle is kind of the closest you can get without having too many issues or possible issues within the manufacturing line. Additionally, I'm going to suggest some reasons in which small cans are not always tall and thin, even though like right here is a good example of cans being tall and thin, and I can think of like Monster Energy, Liquid Death. There are a lot of cans that market like the tall, thin soda, quote unquote soda cans that are like really cute when you look at them, but when you're holding them for a while, you realize that they're not as ergonomic as like LaCroix cans. Let me look those up for you. LaCroix cans. Because if you're looking at these LaCroix cans, they're about the height of a human hand, like from one edge of your palm to the knuckle of your thumb. It basically, like when you wrap your hand around a LaCroix can, you're basically encapsulating the entirety of the can there, which makes it, even though your fingers don't touch, it's a more relaxed grip that is definitely more ergonomic for your hand, especially if you're trying to transport it around somewhere. Like if you're on the go and you're holding one of these cans, it's less likely to fall over. It has a good center of gravity, and it won't like blow away in the wind because it is still pretty heavy. It's also um the pop tab, the pop tab design of these kinds of cans makes it it's way easier to have a good amount of space to drink from when the diameter and radius of the can are bigger, which doesn't really matter what the height is of the can as long as you have a big enough spout to drink from it, which is why I feel like us as humans, when we analyze how economically like valuable something is, like since creating these cans in a cheap way, making them for a cheap price is less people are likely to buy that because they're kind of looking for something that they can drink on the go. And genuinely, if something is uncomfortable to have consistently or to hold, it's going to be kind of a moot product. Like, doesn't really matter how tasty it is, doesn't really matter how much energy it gives you. It really just kind of matters, can humans hold it on the go? Because humans are kind of always on the go, which is kind of what I pulled from this experiment. And I am assuming that's why not all companies have a uniform, like almost quote unquote almost square shape, or a uniform quote unquote small can shape. So yes, that those were my thoughts. Thank you. Goodbye.